Hey, good morning, everybody. How are you? Okay, so here's the deal with the solutions chapter. Time out. We're done. We're just going to move right along. And we are going to move into this guy right here, chapter 8 acids, bases, and salts. The reason why we're going to talk about salts is every time I say salt, everyone thinks one thing, the stuff you put on like French fries and whatnot. And there are actually like millions and millions and millions of different kinds of salt. And actually, you can't talk about salt without talking about acids and bases, and you can't talk about acids and bases without talking about salt, and we will find out why later on. But first, before I get going, there's a couple there's a little bit of housekeeping I want to tie together. First, homework. You guys are doing awesome with handing in homework. It is way more convenient for me if you can upload it into the Google Classroom. That way, it's just like more organized because I have 40 students, everybody, and each of them sending me emails at all hours at all the time, and it's really hard for me to like keep track of things and keep stuff organized. But whatevs, man, we're gonna do whatever works. So if like uploading it doesn't work, emailing is just fine. However, I'm gonna ask that if you do email homeworks, what I'm finding really helps is if you could put the name of the homework up in the subject. That way I have an idea of what it is, so that like when I'm sifting through 100 emails in one day, I have a better idea of like what goes where. That would be super awesome. And the last thing I want to say before I get going, like there's the last third bit of housekeeping. Man, dude, look, I'm so impressed with you guys. I honestly don't know if I was your age, if I could actually sit my butt down and get this work done at home. I would. Man, it's a challenge for me to sit my butt home right now, and I'm supposed to be like adulting. But I just want to say I'm really proud of you guys for like actually doing this. I am proud of you. Keep it going, cause man, the Regents is going. We're in like the land of like COVID weirdness, but Regents is coming, and so is your college. So this is like actually a really good test run for college where work just comes at you and there's nobody there to babysit you, and you just gotta like dig in yourself to get it done. You guys are awesome. You guys are awesome. Oh yeah, but the last thing I want to say about that is what's gonna really help you guys out, I think. And like I think that the first couple assignments it wasn't so good. Round two, you guys are getting way better at time management, so you don't wait till the very end because I can't help 40 people all at once. I have like 30, I think 30 Regents and 10 Chem 101ers. So it's like I just can't answer 40 people's questions starting at 11 o'clock when it's due on midnight. You know what I'm saying? Round one was a little rough, but like I said, round two was way better. So I'm just reminding you that managing your time is going to be huge, like a huge advantage for you. So that being said, let's move on to acids and bases. So let's look down here. So here's the deal. In water, in every sample of water, it's just like water molecules are bouncing around all over the place, right? And they're smacking into each other. And we learned in the other chapter with like kinetics and equilibrium that when molecules collide with enough kinetic energy, like with enough force, they're going to break apart, right? Same thing happens with water, except there's a weird thing with water because of course water is weird. It's water. But I want you to look down here. Wait, I've got this awesome thing right here. You see this right here? H2O. Two waters, right? When two waters collide, what very often happens is they smash together so hard that one of them breaks in half. You dig? Problem is, like, there's not a half, there's only three parts. So a hydrogen breaks off. And one of the hydrogen breaks off of this guy, well, I shouldn't say this guy. A hydrogen breaks off of one water and kind of gets stuck into another water. Because if you remember the Lewis dot diagram of water, there are two electron pairs floating around, and it's able to like grab a hold of that hydrogen and it breaks off. So these two waters break apart. One loses its hydrogen and turns into this OH thing, right? And we call that the hydroxide. And the other, the one that sort of grabs a hold and captures that broken off hydrogen ion, which by the way, a hydrogen ion, an H plus, is merely, it's basically like a naked proton. It's a proton without any electrons, and it gets gobbled up by this water. You follow? So two waters collide, a hydrogen breaks off one of them, the broken piece floats off, and we have a hydroxide. The other water that absorbs that hydrogen becomes this thing, this H3O. Now, if you also notice, this is a 1-to-1 ratio. In pure water, you will have 1 H3O, we call that a hydronium, to 1 OH, we call that a hydroxide. They're perfectly equally matched. You dig what I'm saying? But I also want you to notice that, like right here and right here, you see the charges? So one is positively charged, one is negatively charged. Guess what they're going to do if they smash into each other? They break apart. This guy's positive, this guy's negative. How long do you think they're going to stay apart? Yeah, not long. So in like the blink of an eye, boop, they go right back to being waters. You guys get what I'm saying? That's why we have this thing right here. I'm pointing to the screen. I can't help it. This is the equilibrium symbol, because this is something that's at equilibrium. It's constantly happening and then unhappening in water. Every bit of water. There is no sample of water where this process is not happening. So in purest of pure water, you will have hydronium ions. You will have hydroxide ions, but the thing is they are equally matched, so we call them neutral. It can't be acid or it can't be base. And the thing is, if you look here, oh, these brackets right now, and this bracket right now, like these brackets, those brackets mean concentration. So anytime you see like brackets, that's like chemistry style for saying concentration. So the concentration of your hydronium ion is going to be exactly equal to the concentration of your hydroxide ion. Right? They're going to be like, it's like a 1-to-1 thing. And in pure water, why? Because in nature, their concentrations are 1 × 10⁻⁷ molar. In other words, in pure water, you will always have 1 × 10⁻⁷ moles of hydronium and 1 × 10⁻⁷ moles of hydroxide in pure water. And if you notice, like I said, they are at a 1-to-1 ratio. So one isn't taking over the other, and that is why water is neutral, because it can't go either way. Because here's the thing. This thing right here, this hydronium, that is what makes acids acidic, or acid. That's the acidy thing that makes acids. And this guy right here, the hydroxide, that is what makes bases all like, you know, basic-y and stuff. Does that make sense? I hope so. Because look, defining what an acid and a base is not clear-cut, straightforward as much as we would like. So to say, oh, this is an acid, that is a base, what we really need to do is first dig into what the characteristics of an acidic solution or a basic solution are. And when we do that, we need to keep this basic process in mind, that water is always breaking apart, making hydronium and hydroxide ions. Does that make sense? That one's the hydronium, that one's the hydroxide. Okay? Hydronium. It's basically a water with a naked proton in it. And in this hydronium, the part that's active, the part that's doing things, is that hydrogen ion, or the H+, or the proton. There's like 3 different ways to talk about it. And we will be talking about all 3 different ways, interchangeable, just to confuse you, because you know that's what the Regents people are going to do, because it's confusing, so why would they not do that? Because. Alright, so here's the deal. First thing we're going to do are talk about the characteristics of acidic solutions and basic solutions. Now we're going to end it there for today, but that's kind of like, that's the starting point, right? We're going to talk about what the characteristics of an acidic solution and basic solution are, and then once we understand like what is a basic solution, what is an acidic solution, then we can dig into what is an acid and what is a base, because like I said, it's, you know, we're talking about nature, so it's not perfectly cut and dry, black, white, this acid, that base. Depends. So let's get started. First thing we're going to look at are acid solutions or acidic solutions. So here's the deal. What makes something an acidic solution is this right? Yeah, there are more hydrogen ions. Do you understand what I'm saying? Oh yeah, and this thing, this hydrogen ion, this is another way of like writing out the hydronium. So hydrogen and hydronium, these 2 things are interchangeable, like I said, because there's like this hydrogen ion is the part of the hydronium that's actually doing the work. It's actually making acidic things acidic and whatnot. Do you guys get what I'm saying? Right. So an acidic solution is simply a solution containing more hydrogen ions than hydroxide ions. Does that make sense? That's really all there is to it. That's what makes an acidic solution an acidic solution. If it gets really, really, really acidic, there's like a whole lot more hydrogen ions than hydroxide ions, and that is it. That's all there is to it, right? So another thing is that this hydrogen ion, it won't float around alone by itself in actuality, right? In reality, it's not a lone naked proton floating around, because a lone naked proton is really unstable. It's going to do everything it can to cover itself up with electrons. It's like if you went to school naked, you would do everything to cover yourself up like right away. It's sort of what that naked proton is trying to do. So it embeds itself in the closest water that it can, and usually it's the water that was in that collision. And so this hydrogen ion bonds with water to make the hydronium ion, which is H3O. And like I said, these two things are completely interchangeable, right? These two things completely interchangeable. But what's important is that this thing, the hydrogen ion, is the one that's doing the work. You got it? Oh, also, if you go to table K in your reference chart, it has all of the fancy and important acids and bases, or K is acids, that you're going to need to know. And something that you'll see in all of them all of the time. Oh, hold on a second. Let me get my thing here so I can... Oh, I guess I'm down here. Hydrochloric acid. Watch. You see what hydrochloric acid starts with? You see that? You see that right there? Right. See how it has a hydrogen ion in it? How about sulfuric acid? H. Oh, why did I do that? That was a bad one to choose. Stupid subscript things. Sulfuric acid. Do you see how there's you see how it's starting out with a hydrogen? That's what makes it an acid. Great. Also on table K, you'll see an acid, but it might be a little bit weird. It's whatever ends in this. Let's do that. That's an acid. That's an acetate ion. So that is sodium acetate. We're not gonna really get into like what's going on with it and whatnot, but basically what I want you to see is that anytime you see that is going to be an acid. It's an organic acid, and we will dig into why that's an acid and how it works later. I think that's like chapter 11. But right now, all I want you to do is recognize that COOH is an acid, because when you put it in water, that H is the one that sort of breaks off and makes an acid. And the other one that's really weird is carbon dioxide. It's not that carbon dioxide itself is an acid, but when you dissolve carbon dioxide in water, it makes an acid, which is one of the big problems with the whole global climate change. Is there's so much more carbon dioxide in the atmosphere that it's dissolving into the ocean, because atmosphere touching ocean, and when that carbon dioxide dissolves into the ocean, it acidifies the ocean. And when it becomes acidic, it like dissolves the coral shells around our little teeny buddies. It's like if you take it's like if you were ever young, take an egg and put it in vinegar, and you can like dissolve the shell off of the egg. It's the exact same process, only it's just slight. And what we're really worried about is, one, losing coral reefs because they're beautiful, but also the zooplankton that are in like that first meter or two of the ocean have a little shell made out of the same stuff as coral to protect themselves. But that's also where the most carbon dioxide is, so it gets the most like acidified, and it dissolves those shells, and those little critters can't live, which we might not care unless you breathe oxygen, because that is where a massive amount of oxygen in our atmosphere comes from, those little like critters floating around in that first meter or two of ocean that do photosynthesis. So yeah, bummer. Oh, hey, I totally forgot one of the things I meant to say at the beginning, darn it. But look, this is okay. We're just starting out. You might be wondering to yourself, Stu, where are my notes? You didn't upload any notes, Stu. Right, because here's the deal. We're going back to old school, just like I did way back in the day before, I don't know, like when I first started out. Y'all are going to write out the notes. So everything I write, you write. So you should have, let me back up here for a minute. You should have acids, bases, and, well, first up here, you should put your name, like up in here somewhere. And then acids, bases, and salts. You should write out this equation right there, because that equation right down there, that one, That one? That equation you're going to need to know. You'll see it again and again. And same with that concentration thing underneath. The hydronium is going to be equal, the concentration of hydronium is equal to the concentration of hydroxide. It's always 1 times 10 to the minus 7. You're going to need to know that memorized in your brain. So write it out, put your name on it, and hand it in as if it was like a regular homework assignment. Okay? So you're going to handwrite your notes out this time, just like I used to do. Welcome to old school Stu. A new 21st century version or something like that. Anyway, let's go back to where we were, which is down here, and let's talk about base solutions. So, a base solution. Let me get them some space here. A base solution, if you can believe it, is a solution that has more hydroxide ions than it does hydronium ions, and that's all there is to it, right? The hydroxide ion is what makes bases act, that's a terrible arrow, is what makes bases act like bases. Or another word is alkaline, right? Like you ever hear alkaline batteries? Alkaline batteries are filled with hydroxide ions. So the word base and the word alkaline are interchangeable. Alkaline is like the olden day version, and base is the like more modern. But we still use alkaline all the time. I don't know why, but we do. So a base solution is simply a solution that contains more hydroxide ions than hydronium ions. That's all there is to it. And if you go to table L in your reference table, you're going to see a whole bunch of examples of bases, like this. Let's check it out. Sodium hydroxide. You see how there's a sodium here and then a hydroxide? That's how we call it, sodium hydroxide. You see how it has an OH? You dig? It's an OH base, because when you put that into water, it makes an OH. Can you believe it? It makes hydroxide. I don't know. Wrap your brain around that. Another really common one. Hey, Wyatt, what's up, bud? This one. Subscrippy 2. That is calcium bonded to hydroxide. We call that calcium hydroxide. That's a base. Do you see how complicated that is? Oh, there is one exception that you must memorize, because it's the exception. But you don't even need to memorize, but you need to recognize, maybe that. And it's on your reference table, so it won't be that hard. Is this? Oops. Hold on, let me get out of subscrippies. Bam! NH3. You got to know that this stuff, ammonia, that is a base. No hydroxide in it though, right? I know. We will get there. I'll show you how that works when you put it into, but the thing is, when you put ammonia into water, it makes a basic solution. And we're defining a basic solution as anything that has more hydroxide than hydronium. And you put ammonia in water and it makes a whole bunch of hydroxide, like a whole bunch of hydroxide. That's why ammonia is such a good cleaner. I don't ask anymore. All right, so you guys got it? Are we good? Or like what an acid solution is, what a base solution is, a basic solution, not like so basic, but like basic, like chemistry basic. Okay? All right, moving right along. Oh, yeah, salt. This is our third definition of the day. What is a salt? Well, here's the deal. A salt is defined as oh, sorry, let's space that out. A salt is defined as the leftovers of an acid-base reaction. This is a really long, complicated version, right? An ionic compound made up of an anion from an acid and a cation from a base. My people, salt is the leftovers of an acid-base reaction. Let's review. Let me get out my little pencil thingy here. All right, this, I don't know if you can imagine, that is an acid, right? This thing over here, this is a base, right? We can see that this is the acid because it has our hydrogen ion. We can see that this is the base because it makes the hydroxide ion. Are you guys with me on that one? So here's the deal. This OH and the H, anytime you get two hydrogens and an oxygen near each other, because then, let me back up again. These are all aqueous. This is all going to happen inside an aqueous solution. So being like lazy as I am, I didn't put aqueous in everything. So we're just going to assume from now on that everything is aqueous. So these are going to be dissolved in water. And we'll have a hydrogen ion and we'll have a hydroxide ion. And you know that anytime two hydrogens and one oxygen get together, they are going to make water. right? So this OH and this H, the hydrogen and the hydroxide, they make water. Does that make sense? And so this hydroxide, it's gone. It's like not really there anymore because it's now making a water. Same with that hydrogen. It's kind of like gone because it's being used up to make water. Ooh, wait, I was going to use purple, but that's gross. That's Sentinels use purple. We don't use purple. So what's left over in the water? Well, we have sodium left over in the water, and we have chlorine left over in the water. Do you guys understand what I'm saying? So what happens is the sodium and the chlorine are just left floating around. You boil off all the water, and you're left with salt. So here's the deal. Hydrochloric acid, HCl. You guys know that is an acid. We've all seen what happens if you pour go look at like acid burns. Acid does horrible things to you. It can burn you terribly. Bases, man, if you think acids are bad, bases are worse because bases, like I said in lab, they are made to break polypeptide bonds, which is what we are made of. This is what holds all of our proteins together. So if you were to, like, say, take a glass of sodium hydroxide, good and concentrated, and try to chug it, you probably wouldn't get past the first chug before most of the inside of your mouth became liquid. You cannot mess with this stuff. Hydrochloric acid, it's what we use to digest our food with. Like, these are nasty, horrible compounds that are not good to mess with. However, when you put them together, it makes water, which we need to live, and sodium chloride, salt, which we have to have in order to live, which is, nature being like, I don't know, nature, you know what I mean? All right, so that's what a salt is. This right here, this is your fancy This is your fancy academic definition. It works out great. You can also just say the leftovers of an acid and base reaction. Because when an acid and a base react, they make salt and water. Say it with me. Acid and a base make salt and water. 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 I wish I had so this is where I need my stick to like hit the thing and like make some silly thing song. School's better in school. Although this is pretty comfy being at home, I'm not gonna lie. My cat's and my dog are right over there, so that's good. Right, we have an acidic solution, more hydronium than hydroxide. A basic solution, more hydroxide than hydronium. And we have, for 3, a salt, which is the leftovers of an acid-base reaction. Got it? Let's move on. Because now, I want to talk about the characteristics of acids and bases. Solutions. The characteristics of acid-base solutions. And what I've done here is I've divided, so just like cut your paper, like draw a line down the middle. And on this side, I want acids, and on this side, I want bases. And we're just going to like compare them right down the line. And as we do that, we're going to get a better understanding of what makes an acid an acid, what makes a base, and then we can move on for our next lesson on how we identify a compound as an acid or a base based on what happens when we put them in water. Got it? Good. Okay, so an acid. All characteristics of an acid come from the hydronium ion, and all the characteristics of a base come from the hydroxide ion. That was like kind of what I said up above earlier. Hey, Wilder. What are you? Wilder's learning chemistry too. So, I mean, that's one difference. Acids, you can also say H plus over here. You can just say hydrogen ion. That's totally legit. But we will be using hydronium because that's how it actually exists in water. And the hydroxide is actually just a hydroxide in water, and it doesn't do anything special. As far as tasting, we actually are made to love the taste of acidic things. It tastes sour, like Sour Patch Kids, lemons, like pretty much anything citrus. Vinegar, like anything vinegary, like vinegar on your friend. Dude, you gotta get out of here, man. I'm being a teacher. Where was I? Sorry, I had to adult for a minute. Acids taste sour. They're kind of like delicious. Like tomatoes have a ton of acid in them. They're so yummy. We love acids. Actually, vitamin C is an acid. Like we have evolved to really enjoy the taste of acidic things, because a lot of our vital nutrients are actually a little bit acidic. However, if you look down here, bases taste bitter. Not bitter like I don't like that, but bitter like we have a gag reflex to spit it out because it's gonna dissolve us if we eat it. So it's not a real surprise that like evolution says no to bases. Bitter as in like pretty nasty and bad. Do you guys get what I'm saying? Sweet. That's why we eat Sour Patches. If you look at the ingredients of Sour Patches, it's like I think it's citric acid, just like powder form. Yeah, it's delicious. I'm not gonna lie. Ooh, bases. The physical feel. So acids, when you take hydrochloric acid, you pour it on your hand, it feels like water. It looks like water. I don't know if it tastes like water, not going to find out. It does not smell like water, but it looks and feels just like water. Trust me, I know. I've spilled hydrochloric acid all over my hands. Not a big deal. Our skin is pretty good at like protecting us from stuff like that. So it just feels like water. That's why this is nothing. However, bases feel slippery. And a way you can check that out is if you take some bleach, and if you get bleach on your fingertips, it'll start to feel really slippery. Now here's the fun part. The reason why bases feel slippery is because it is a hydroxide ion, right? Let's come back up here for a minute. See that? The hydroxide, it's basically half of a water. And our skin is made to absorb water really, really quick and really easy because, that way it stays nice and wiggly so we can do stuff. And that hydroxide ion is indeed absorbed into our skin very fast from the bleach because it is actually a very like alkaline or basic solution. And that slippery feeling, fun fact, is when those polypeptide bonds that hold the molecules that make our skin together, like when those polypeptide bonds are broken, our skin is turned into a soap-like compound. Feels quite slippery. So we're turning our skin molecules into gross little like soap molecules, and so that's why it feels slippery. And the reason, if you get a little bit of bleach on you, and it'll take like a long time, like you're sitting there like you're rinsing your hands like what's going on? Why is this not? Why? Because it is absorbed into your skin. And so it's like first you have to rinse off the top layer of soap-like stuff, and then you got to rinse off the bottom layer of soap-like stuff while the hydroxide just keeps slowly soaking into your skin. Fun times. Bases are bad. Bad. Yeah. Anyway, that's why bases feel slippery, because they're turning us into soap. So gross, dude. So gross. Oh, yes, here's this. Aqueous solutions of acids conduct electricity, and aqueous solutions of bases conduct electricity. They conduct electricity. Why? Because they are what we call an electrolyte. Look, vocab word. Electrolyte. An electrolyte is an ionic compound that conducts electricity when dissolved in water. So, to conduct electricity, you need ions. You need mobile ions, ions that can kind of move around, which is why metals conduct electricity so good. Highly mobile valence electrons, right? So those movable electrons are literally movable ions. So when there's a potential on this side, it just goes and shoots the electricity like right through it. Same thing when you dissolve ions into water. Those dissolved ions act as little hopping grounds for the electricity to move through. So if it's ionic, it is an electrolyte. In other words, it conducts electricity when you dissolve in water. And acids, they have to make a hydrogen ion. Ionic, you see how that works? And bases have to make a hydroxide ion. Yeah, you see how that works, right? Base, a hydroxide ion, therefore ionic. Acids have to make an ion. Bases have to make a hydroxide ion. It's ionic. That makes it an electrolyte, because that's what they are. I think I'm going in circles. It's still early here. Yeah, that's fine. Alright. Yeah. So this is another thing. Strong versus weak acids and bases. Now this is going to be a little bit different in the lab, like when you're talking, or like in the domain of chemistry, than in like regular people world. Strong and weak is much different than concentrated, right? Most people think of, and you say, "Oh, that's a really strong acid." If you say it to a non-chemistry sciencey person, they're going to think concentrated. If you say it to a sciencey person, strong and weak mean very, very different things. So for us, in our perspective, from like this perspective of chemistry, strong here means that when you put that stuff into water, it's going to conduct electricity like really well, like really good. It's like it does its thing very well, independent of concentration, right? Because concentration just means how much there is. When we talk about strong versus weak acids and bases, it basically means how well they break apart in water, and therefore how well they can conduct electricity. Does that make sense? So weak acids and bases, they do not conduct electricity very well, kind of like regardless of what their concentration is. You can have a highly concentrated weak acid and it'll still be a poor conductor of electricity, relatively speaking, to its strong counterparts at the same concentration. So strong acids and bases will conduct electricity very well at comparable concentrations as compared to weak. Again, this is all kind of relative. And weak acids and bases conduct electricity relatively poorly at the same concentrations compared to their stronger counterparts. Right? So again, strong versus weak in science, when we're talking about acids and bases, does not mean whether it's concentrated or dilute. That's why we have molarity. That tells us how concentrated it is or isn't. Yeah? Yeah, moving on. All right. Acids react with bases to form water and salt. Bases react with water to form water and salt. Because remember the little song? We almost had a little song going on. I was like kind of feeling it there for a minute, little acids and base make water and salt. I said acids and base make water and salt. I said acids and base make water and salt. I said acids and bases make water and salt. I said acids and bases make water and salt. I said I think that's it. That just happened. Video. That's on video. You just saw the birth of a song. Acids and base make water and salt. I said acids and base make water and salt. I said acids and bases make water and salt. Acids and bases make water and salt. Acids and bases make water and salt. Oh god. I can't put this on the internet. I can't do that. Nope. Not happening. It's one thing making an idiot of myself in the classroom. It's different when other people... I'm not posting this. Alright, anyway, neutralization. We call that neutralization when acids and bases make water and salt. Acids and bases make water and salt. Acids and bases make water and salt. Because they're neutralized. There's no more acid. There's no more base. They're gone. Right? Remember, like in the way up in the up above thing, we had hydrochloric acid and we had sodium hydroxide. When they mixed together, was there any acid left? No. Was there any base left? No. It was neutral. Like neutral means no acid, no base. Like they're gone. So that's what we call neutralization. It's a It's a reaction where the acids and the base react. Right here, it should be like completely, but sometimes it doesn't go to completion. But for us, it's going to be to completion, where an acid and base react to form water and salt. And remember, this water right here, the water comes from the hydrogen from the acid and the hydroxide from the base. Because man, hydrogen and hydroxide, that's it, man. Water, so stable. Once it forms, it's not going to break apart. And the salt, again, this stuff, it's just the leftovers from the acid and the base. Got it? Good. Okay. Moving on. Oh, look. Acid, base, water, salt. This is an example of an acid base. Let me do some editing right here on the fly here. If you don't know what this is, you have to leave. So this is your base. This is your acid. Once again, this hydroxide and the hydrogen, these two things are what come together to form the hydrogen. And then the leftovers, the sodium and the chloride, are like that's kind of what makes the salt. You dig? I mean, that's really it. If you need help identifying the what salt there is, what I usually do, again, because my eyes are not really all that great, what I often do is I scribble out the hydrogen, because that's gone, that's in water, and I scribble out the hydroxide so that I don't see it anymore. And then whatever is left, this is my cation, That's going to be the plus one because it's plus here, so it's going to be plus in the final one. And over here, this is my negative ion. So that's how I tell what my salt is going to be made out of. So if you're not really sure, if you're having a hard time figuring out, like, what salt do I make? Just scribble out the hydrogen and scribble out the hydroxide. The leftovers, that's it, man. That's what your salt is. And this process that you see right there, that's your like quintessential neutralization reaction, because there is no more acid, there's no more base. It's all just happy neutral salt water. Well, you should gargle with if you have a sore throat. Okay. All right. All right. Let's look at a few examples here. So here's one right here. So we have magnesium hydroxide, right? So oh, look, this is even balanced for us and everything. So what I want you to see here is, you see how there are 2 hydroxides there? Right. That's why we needed 2 hydrogens. And so in this case, our hydroxide and our hydrogen, these 2 things are going to come over here, and they're going to make us the water. Like, are you guys with me on that? And then what we're left with is magnesium and chloride. And if you want to know what the charge of magnesium is, you can either memorize it or go to your periodic table on your handy-dandy reference charts and know that magnesium is actually going to be a +2. And chlorine is a -1. Now, a lot of people start looking at chlorine and they're like, how do I know what it's going to be? There's like a million charges for chlorine. I'm so confused. Don't be confused, because chlorine is on the right-hand side here. You see that? Right? So if it's on the right-hand side, that means it has to be negative, and there's only one negative option. So because magnesium is a +2 and chlorine is a -1, our final chemical formula will be MgCl2. Got it? Because this is +2, it's -1. There are 2, so we have -2 in all. Got it? Great. All right. Let's go to the next one right here. This next one, we have HCl, hydrochloric acid, and potassium hydroxide. So this is your acid. See how it starts with an H. This is your base. See how it has an OH. Now, an acid and a base makes what? Yeah, you said it. And now we got to figure out what the salt is. How could we possibly figure out what the salt is? Well, I'm going to tell you. First thing I'm going to do is I'm going to scribble out my hydrogen and my hydroxide so my eyeballs can actually look and see something. Oh, shoot, did that. All right, so this is my acid. It's going to lose its hydrogen. And this is my base. It's going to lose the hydroxide because they both went in to make the water. Gone. Sweet. So I'm left with potassium. Potassium is a group 1 ion. So I know that it's going to be a +1. Chlorine, always a -1. Also, if there's only 1 chlorine attached to 1 hydrogen, we know that hydrogen is always +1. So that has to be -1 to be balanced, right? And we know that hydroxide is always -1. So if there's only 1 potassium, it has to be +1. So my salt will be potassium. Ooh, look at me try to draw with the mouse, right? Potassium, it's my cation. KCl. Okay? You following that? Easy peasy lemon squeezy. Acid and base mix water and salt. Oh. Oh, guys, look at this. Why would I do that to you? This is just evil. But look, I left these in here to help you balance them. But you will be expected to do this. These are just the notes. You will need to do something just like this, but it's not as hard as you might think, because look, it's an acid. See how it starts with a hydrogen? Look, hydroxide. I'm pointing to the screen again. Jeez. Look. Hydroxide, acid, base. I think I know what one of the products is going to be. I think I can guess this. I'm not going to. You guys get what I'm saying, all right? First thing it's going to make is water. Now, over here, this might be a little more tricky, but you know how to do this. Remember the whole puzzle piece lab? You guys own this, so don't tell me you can't do it. It's the same thing, just in a different context. Step 1. Follow me. I am going to, I'm going to get rid of this hydrogen. and I'm going to get rid of the hydroxide so my dyslexic stupid eyeballs can see what the heck I'm looking at. Awesome sauce, right? So there's H2O. My positive thing looks like it's going to be a calcium. Now, I don't have my reference chart here with me, so I'm feeling a little bit lost. I don't know what the charge of calcium is. Oh no, did I just lose the thing? Yeah, all right. So, I know that calcium is, I can't, I'm not sure what the charge of calcium here is, but I do know that each hydroxide is -1. So if each hydroxide has a charge of -1 and there are 2 hydroxide ions, how much charge do I have in all? 2, right? So if this all together, if I have a charge of -2 in all, that means that my calcium must be a +2. See how that works? Don't even have to look it up. Same thing with the PO4. I honestly don't remember what PO4 charge is. I'm lying, but I'm pretending. I know that that's going to be my anion. So I'm going to do P. Does it make sense? But I don't remember or know what the PO4 charge is, but what I do know is that each hydrogen has a charge of +1. There are 3 hydrogens in all. How much positive charge do I have? Well, 3 hydrogens, each is +1. I have +3 in all. So if this is +3, the PO4 has to be -3. See how that works? And now, boop, 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 we're gonna do the crossover, the drop and flop, the whichever you'd like. So we're gonna take this number 3. I'm gonna put it down here. I'll have 3 calciums. I'm gonna take this 2 and drop it down here. And guys, I'm gonna just hope. Son of a dinkleberry. All right, I'm gonna hope you remember that there are not 42 oxygens here. No, 9. No. Right? There are not 42, and that is silly. But you remember what to do, right? You remember what you need to do to indicate that there are 2 PO4s, not 1 phosphorus and 42 oxygens. That would be stupid, but 2 PO4s. Brag it. Brag it. Well done. Yeah? Okay. Hang in there. We're almost done. All right, so 1 or 2 more last little things. Acids. You know how like indicators? Yeah. Okay, so indicators are things that change color when you put them into an acid or a base. It's like pool testing kits. You all see those things that'll like strips, and you like dip them in the pool water and they change color to tell you if everything is good. That's all an indicator is. And what I need you to know is litmus. I don't know why they like litmus, but it's like left over from the 17 and 1800s, and they still want you guys to really know what litmus does. I don't know. There are majillions of different kinds of indicators that we use, but for some reason the New York Regents really want you to know what color acids and bases turn litmus. I think it's because it's like the most historical one that they used to use back in the day. They call it the litmus test. It's like an idiom now, right? You stick litmus, boop, dip it in. You know right away if something is an acid or a base. Here's the thing. Acids cause indicators to change color. Oh, I guess that's why I did that. Bases cause indicators to change color, right? And that's the thing. But with litmus, bases turn litmus. Wait, acids. I'm sorry, wrong side. Acids turn litmus paper red. Bases turn litmus paper blue, right? Acids turn litmus paper red. Bases turn litmus paper blue. All right, so bases turn it blue. Bases turn it blue. With me, go. Bases turn it blue. Bases turn it blue. That's something I do for you to help you remember. When you take the Regents, the summer. I'm reaching for that one. Okay, so bases, with me. Bases turn it blue. Bases turn it blue. That's how you remember. I mean, that's how I remember. Bases turn it blue. Bases turn it blue. Now, so we got acids and base make water and salt. Acids and base make water and salt. Acids and base make water and salt. Bases turn it blue. Now, how are you going to remember that acids turn litmus red? This is the most silly. Chloe, if you're listening out there, I love you for this. I wish I could take credit for this, but this one was from Chloe, and I'm props because I can't get this out of my head. It's hilarious. Do you know how Chloe remembered how the acids turn red? Because baboons have red acids turn litmus paper red. You thought I was gonna say a bad word on the internet. Remember, baboons have red acids turn litmus paper red. Baboons have red acids turn litmus paper red. That is, that's hilarious. I think it's funny. You don't have to. Okay. Oh, this is also a funny thing. Acids. So acids in Hollywood have sort of a funny thing. Like, you know, people are always dumping acids on people. Like, oh, I'm gonna melt. But really, man, you want to melt someone? Not acids. However, if you want to melt metal, acids are where it's at. Because acids will react with metal, well, most metals, and form hydrogen gas. And the only way you can know which metals is by looking at your table J in your handy dandy reference table. And all that means is like, so table J is a big long list of metals. Hydrogen is way down here toward the bottom. All the metals above hydrogen, they will react with an acid and make hydrogen gas, and the metal just totally dissolves. It's pretty awesome. Yeah. Yeah. I'll see if I can find a demo in this one, but let me see what else. So this is the example here where zinc, a metal, if you look at zinc on table J, zinc is like way up here and hydrogen is like way down towards the bottom. So that indicates that zinc with an acid will make hydrogen gas. And the way that we know what the products are going to be is you take this hydrogen right here, and then you do what I do, and you get rid of the hydrogen, because all the hydrogen is going to go into hydrogen gas, and the leftovers are going to be zinc and chlorine, and you end up with zinc chloride. Does it make sense? Awesome. Okay, so here's what I want you all to do. That's it for today. As if that wasn't enough, my God, I just won't shut up today. 3 homework assignments. Water, the neutral substance. You know what to do. Work goes on a separate piece of paper. Upload it. Do. Intro to acids and bases. It's multiple choice. These are like, these are all old Regents questions. I just want you to do them. You know how this goes, guys. I really want you to do this because this is how you're going to get ready for the Regents. These are the kinds of questions that you will be seeing. If you have any questions, shoot me a text, shoot me an email, post it on the classroom, probably better, because I'm finding myself answering the same question like 10 times at least. So if you have a question, post it on the classroom. I'll answer it, and I guarantee you more people are going to be like asking that same question. And third thing, the notes that we just went over that I said out of my face and that you looked at down in here with these things written out on a separate piece of paper. That's 3. Oh, and I'm sure there's going to be some kind of crazy online reading and stuff you have to do and look at and stuff. But just remember, I don't want this all done in one day. This isn't, I don't expect you to sit down and do 3 hours of homework all at once. This is made to be spread out over, like, some time. So learn how to manage your time wisely, a little bit each day. If you forget all during this like whole like covocation, what are you guys calling it? This whole like lockdown thing or whatever. If you guys forget all the chemistry you learn, but at least learn, but stay and learn and hold on to how to manage your time to get your work done, man, I will call it a total success. Because that's where you guys need to be. So that's it for me for right now. See you in a couple days when we start talking about how we identify something as an acid or a base. All right, man. Bye bye.